All right, welcome back to the second part of lecture 15. In this lecture, we are going to develop the general idea of spatial interpolation, right? If you have worked with time series data, you must be aware of interpolation. Missing values are a typical problem in sample data sets. And whenever the values are missing, one of the ways to deal with them is to fill them back using a statistical approximation, which is also known as statistical interpolation. When we conduct this exercise in space, it is called as spatial interpolation. Remember, however, in space, we have missingness is fundamental because we cannot possibly sample every point in a domain of interest, right? So interpolation or spatial approximation or spatial prediction on locations that remain unsampled is a fundamental problem with spatial data analysis, right? Okay, let's move forward without any further delay. So spatial interpolation is also called as kriging. Kriging is synonymous with optimal prediction. We consider a problem of predicting groundwater level at an arbitrary point in space. So what you see on the right bottom corner of your figure, that you have these three sampled locations, S1, S2 and S3, where you know what is the groundwater depth. And you want to know what is the groundwater depth at S0. Remember, we did this for one dimension. Now we are bringing the problem to the two-dimensional space and we are generalizing it. Okay, a convenient estimator is basically a weighted sum of these values that are available, right? If there was no spatial dependence and I was working with some series of data with no dependence, then GS0 is just GS1 multiplied by 1/3 plus GS2 multiplied by 1/3 plus GS3 multiplied by 1/3. That is to say that, I have these weights, lambda 1 equals 1/3, lambda 2 equals 1/3 and lambda 3 equals 1/3 being multiplied to each of the observed values and then summed together so that I get my value, which is unknown, a prediction for the unknown value, right? Now, in this case, it's a little bit more complicated in space. The first thing is that GS0, that is location S0, which is the unknown location of interest, is closer to locations S1 and S2 than it is from S3. So there is this idea that, S1 and S2 may be a better representation of S0 than S3 just because they are closer to the two. This will basically imply that I cannot possibly have the same lambda i's in case of, when I'm working with non-spatial, non-dependent data sets, right? So I have provided you here a convenient estimator where these weights are a typical method of predicting data, conducting prediction. But here the weights are not going to be equal in the sense of how each sample location is weighed in space. We have this extra component which is 1 minus summation I equals 1 to 3 lambda I times G bar. This extra component is just to ensure unbiasedness of the estimator, which is G star S0. And this also ensures unbiased through the fact that sum of weights must equal 1, right? If I do not include this component, I can't ensure that the sum of these weights will be equal to 1. Right? If you have, worked with constraint optimization before and, you know how to sort of include constraints in Lagrange function, then you can look at G bar as the Lagrange, multiplier and 1 minus, summation I lambda I being the constraint, that summation I lambda I must equal 1. Right? So it's the same formulation, just written out conveniently for our own purpose. So lambda i's are data weights and G bar is global mean. So we have this, convenient estimator. We have data for GSI, we have data for G bar. What we do not know are these weights. So the whole problem in this lecture is going to boil down to figuring out what the weights lambda i's are. So again, similar to what we did in the previous lecture, what if we are working with non-stationary data? Well, if you are working with, let's say there is a domain on the right hand side that where you have these code values. Remember, this data are coming from Michael Perch at UT Austin. We saw a poster where this figure was there, where you have these cores being dug out of earth, at different locations, and there is a domain of interest with, a black dashed line. But what if there are these domains, this larger domain are made up of two stationary domains when, but when they are sort of unionized together, they are clubbed together, all in one is a non-stationary domain because there is a structural break in between. And what if the value that I want to, estimate lies in neither of these domains? So the idea is I must use data in both domains and I must figure out a way to combine them. So the way we go about it is that we write down, YSI as GSI minus G bar for each domain. Okay, so we just reduce or deduct, reduce the total value observed by the domain mean. Remember, G bar will be different in domain 1, right? And it will be, different in domain 2. Okay. So I'm simply reducing the observed values by the global mean in these subdomains, and the residual is what I'm used to is the stationary variable. So instead of GSI, which is a non-stationary random variable, I'm now using YSI, which is a stationary residual. So the problem then boils down to predicting Y star SI, and after I get my Y star SI, I will add this global mean back to the data, right? But so my variogram estimation, my spatial dependence measure estimation will happen with the stationary values, right? So that the idea of intrinsic stationarity is still holding. Okay. Okay, so let's move forward. So now the basic query, like I said, is what should go into lambda I. Here I have, the first thing was, closeness. So how close is S0 and S1 to each other? How close is S0 and S2 to each other? And how close are, S0 and S3 to each other? Clearly S1 is the closest, quite similar, not so farther apart is S2, and quite farther apart is S3. Data redundancy, this is very interesting. Now, data redundancy is the idea of spatial dependence. GS1, see that S1 and S2 are quite near to each other. In fact, the distance between S1 and S2 is smaller than the distance, each of their distance from the unknown location. If there is strong spatial dependence in data, then these two values are going to be correlated with each other. That would mean that although I am looking at two unique observations, the information that can be derived from these observations is not equivalent to two unique observations. This is an idea that we discussed in the beginning of this, one of the early lectures, where we said, what is the effective n prime when rho equals 0.26? Remember that lecture, earlier in this class, right? You can go back and check, where we worked with a one-dimensional Z1 to Zn data. We first did not have spatial dependence, then we introduced spatial dependence, and we found that the data size reduces. There is a reduction in the data, and this reduction is equivalent to the fact that there is correlation in the data, which is reducing the effective amount of information contained in the data. This idea is called data redundancy. And finally, there is direction of spatial contiguity. Now, it is possible that the data have strong, east-west, contiguity than north-south. There is anisotropy, for example. In that case, you are going to have a problem that even though S3 is farther apart or S1 is very nearby, it's really, in the north-south direction from, S0. So these are some of the interesting factors that must come into account when we decide lambda I. So lambda I should be ideally a function of A, B, and C, right? Okay. Now, what are the common weighting schemes? If you have worked with spatial data, commonly what people do is they use these equal weights 1 over n. Like I said, if you have a non-spatially dependent data, you basically go ahead and you put in 1 over 3, 1 over 3, and 1 over 3 to each of these values, calculate the mean, and you say this is my prediction, this is my best guess. The other thing is inverse distance squared. So here you are controlling for distance. You are controlling for distance in a deterministic sense, right? So you're taking the distance, squaring it, providing an index of dependence between these variables that are solely dependent on the distance. The first commonly used weighing scheme, which is just the mean, the global mean in the domain of observed values, does not account for either of the spatial factors, which is the closeness or the data redundancy or the direction of spatial contiguity. The second one that indeed sort of accounts for closeness does not account for redundancy and the direction of spatial dependence. Okay. So, our task is to construct the weights that account for all above criteria and yield an optimal prediction of G0, which we call as G star S0. Right? That's the prediction. So to do that, let's work with stationary data. Consider a linear estimator for d mean groundwater location at level at location S0. Y star I S0, which is the prediction at S0, is equal to summation of all the weights multiplied by the observed locations. Stationary or d mean groundwater level data implies that expectation of y is equal to 0. That is why we do not need the constraint, which is 1 minus summation I equals 1 to n lambda I times y bar. This y bar is equal to 0. So the constraint is automatically satisfied that the weights will the weights will implicitly sum to 1. Okay. And then I have my intrinsic stationarity, formulation, which gives me my, variogram formulation as well, which is 2 gamma h equals expectation of the difference squared. Sorry for the typo there. It is the expectation of difference squared, where we are taking the difference between observed values at two locations, Si and Si plus h, which can be also called as Sj, in general. The estimation variance. So the truth and the prediction, when I take a difference between them and I square them and take the expectation, I get what is called as the, estimation variance. This is the variance of my estimate. This estimation variance can be written as expectation y star squared minus twice of expectation y star into y0 plus expectation y squared. If you are having any trouble, visualizing this, just take what is inside the expectation operator and expand it. Just take the squared, you have y star S0 squared plus y S0 squared minus 2 y star S0 y S0. Because expectation is a linear operator, it enters the brackets and applies to each of the terms individually. Okay, and that's it. That's all that you're seeing on the right hand side here. I'm going to expand these things a little bit further. So what I'm going to do is I'm going to take y star S0 and replace it with y star S0 is nothing but summation I lambda I y Si. So I'm going to just substitute the unknown value with the weighted sum everywhere that I see it. And then I'm going to expand it. So I'm keeping the expectation operator, as it was, and I'm going to now expand these things. So I have, because y star, I have expectation yisi squared minus twice some expectation of summation of lambda I ysi whole squared plus summation of lambda I ysi times ys0, which is the truth, remember, plus expectation ys0. Now, this summation yi lambda I yi squared can be written as summation, double summation y lambda I lambda j ysi and ysj, and similarly I expand this further. Expanding this thing further, I take the expectation operator in. It's a linear operator just like the summation, so it sort of starts entering in and it goes and applies it to the random variables, right? So these are all constants, lambda I lambda j are constants, and so the expectation operator moves right in. Similarly, in the next as the next component of this summation, the expectation operator just keeps moving in as you see it. Now, finally, this expectation yi ysj, when remember the mean of y at si is 0, right? Because it is a residual. I'm working with a residual. So because the mean is 0, the expectation of the product of ysi and sj can be written as the correlation, the covariance between si and sj. Similarly, in the second component, I can write at this expectation ysi and ys0 as the covariance between si and s0. And because again y bar is 0, I can imagine all of these as written as ys0 minus y bar the whole squared, right? So because of that, I can write this as simply variance of y at s0, which is the unknown location, being c0. Because you are working with stationary data, the large scale variation is same everywhere. It's a stationary variance scenario, right? So C0 applies to unknown locations as well as the known locations. So what happens is that the last term turns out to be the large scale stationary variance, which is the SIL of the variogram. The first term is about data redundancy and the second term is about data closeness. So we have accounted for data variation, which is the second moment in data. We accounted for redundancy and we also accounted for the data closeness. So we have all the factors now in, that I wanted to account for. So let's move forward. So what is the next step in retrieving optimal Kriging weights by, optimal Kriging weights? What we do is, now that we have a sample, estimation variance of the predicted ys0, what we do is we want to minimize this variance. The lesser the variance, the more accurate my prediction. And when I minimize this variance, I basically choose these weights lambda I. And automatically these weights will be a function of redundancy, closeness, and the large scale variation in data, because the estimation variance is a function of these three factors, right? So I set up my objective function here. I write down my first order conditions. I have n simultaneous equations. I have n unknown weights. So I have n equations and n unknowns. Okay. It turns out that, you will have a very convenient sort of a formulation of weights, which we will see in the matrix form going forward. But the idea is that I will have my lambda I star, which are the optimal weights, and remember, these weights account for data redundancy, they account for closeness, and they account for large scale variation in data, right? So unlike the deterministic weights, which are the inverted distance squareds, although they are accounting for distance, they are not accounting for large scale variation in data. They are not a random variable based understanding. It's a deterministic understanding of the world. It's a physical understanding of the world, that just by looking at the distance between two locations, I can say what values will be realized at those locations. That's a very limiting idea, even intuitively, I suppose. I'm sure all of you can understand that. Okay, so let's move forward and look at an example. go back to our example where we started so that we can understand this process with the example as well. So we have these three sample data points, S1, S2 and S3 locations, where the sample data points are G of S1, G of S2 and G of S3. The main objective that I have as an analyst is to be able to predict the value of groundwater level at location S0. Okay. The first thing I must do is assume spatial stationarity. Okay. If it is non-stationary, I should create a filter, construct a filter, defilter, apply the filter to my data, detrend it, sort of mean it, remove all the non-stationarity, and then, work with the residual. So here I'm going to start by assuming stationarity in the data, okay? But it's an imperfect assumption which almost always need not hold with the real world data. Then G of S0 is nothing but the weighted sum of all the available values, which is lambda I GSI summed across all three values, that is summation I equals 1 to 3. Our objective here is to figure out the optimal weights lambda I star. The first thing the hint that we have from our exposition previously is that we have to minimize the estimation variance. We minimize the estimation variance. So we have to then figure out, the estimation variance and try and minimize it. So these first order conditions, as they were in the previous slide, they will turn out to be very convenient. So the first condition is lambda 1, C S1 S1. Remember, this is nothing but, C0. This is C S1 S2. So this is C S1 minus S2, right? This is going to be dependent. This is the covariogram at lag S1 minus S2. And this is a covariogram at lag S1 minus S3, which is equal to the total covariogram of lag between S1 and the unknown location S0. When you look at the first order condition, it's going to be very easy to write the second and the third. They're going to be just cyclic. That is, I will just change this S1 to S2 everywhere, and I will get my, second first order condition with respect to lambda 2. With respect to lambda 3, I again just replace the 2 with 3 in the first component of these covariogram devices, and I'm done. Okay, so it's just a convenient form because, it's just because of the specification of the covariogram. Now the point is, where do these values come from? These values are going to come from the variogram model. CSI-SJ is C0 minus gamma Si minus Sj. This gamma is my variogram model. This C0 is the SIL, which is also estimated from data. So these values are all on the left hand side are just data. I can say data driven. This is data. Okay, and these here are unknowns, right? So lambda 1, lambda 2 and lambda 3 are all unknown. These are variables. And what about CS1 S0? Well, this is too data. I mean, this is nothing but C0 minus gamma S1 minus S0. Although I do not know G of S0, but I can calculate the length or the H vector or the distance between S1 and S0. That's not too hard. I know these locations deterministically, right? So all the components, right, can be backed out from data by, estimating the variogram model. That is why we studied in lecture 14, that is before we came to interpolation or kriging, we first studied the variogram model. The variogram model estimation, fitting a model, goodness of fit criteria, and so on and so forth. Okay. Now for this example, I can write this system of equation, which is written as linear equations, into a matrix form, which is again a linear form. So I have all the redundancy factors CS1, S1, blah, 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 and large scale variance sitting in this matrix called as a redundancy matrix R. These are my unknown lambda vector, right? This is lambda 1, lambda 2, lambda 3, which is the unknown vector. If I get this vector, I am done. And finally, I have the closeness matrix C, which is the closeness between unknown and known locations. Lambda star is just equal to R inverse C, which is pretty clear. Because we are taking an inverse of R, we need that the R determinant of R is non-zero. Otherwise, the inverse cannot be calculated. Of course, you can, there are some advanced topics like pseudo inverses, but I'm not going there in this course. We will also require R to be a positive definite matrix to ensure a unique solution for lambda star. Okay, so if we are to get to a unique solution, we also require our R matrix to be, positive definite. These are very important, theoretical underpinnings. When you will do all of these things with software, when you study R sessions and ArcGIS sessions, we will do all of these things on software. You are not going to be actually calculating these things. But oftentimes when you actually estimate these things, the software just doesn't stop the loop and it doesn't give you the weights or doesn't give you the estimate. If the software does not produce final answer, where do we go? Well, we go back to this black box or the theory and try and figure out what may be going wrong. Well, what may be going wrong are either of these conditions. That is why, the functionality of how the process of getting to the optimal weights and the optimal prediction is as important as learning the syntax of a software. Okay, so although none of this is done manually, but going over it manually is very, very useful. So I encourage you to at least twice go through each step of a optimal kriging estimator, starting from the example to this more generic form in the 2-dimension. Okay. All right. So some sort of, notes to end the lecture. First, the kriging weights and consequently the kriging estimator accounts for distance of information, configuration of data, the spatial configuration of data, and the structural continuity in the data, right? It is a very sophisticated estimator. Okay. The kriging estimator is unbiased. That is, the value that you're going to get is going to be in expectation the same as the truth. The kriging estimator also minimizes the variance of estimate. This is by definition, right? The definition by which we back out the kriging estimator or kriging weights is by minimizing the variance. And the measure of the kriging variance, that is sigma squared E as 0, is going to be the lower than the SIL, which is the large scale variation in data. So the variance of the predictor, the optimal predictor at unknown locations, is going to be by definition smaller than the large scale variation in data. It's a property of the kriging estimator. Okay. With that, we are done with spatial estimation. Going forward, we are going to move to the last module in this course, which is about spatial regression, and I've titled it as spatial econometrics. Here we are going to first do a recap of a regression model, how to interpret it in space, what differs, and then we are going to move towards, as a next step, we will integrate the variogram. We'll see how the variogram model can be integrated in the spatial regression model, right? And then finally, we will move from, we'll learn the theory of moving from, correlation to, causation. We remember, again, spatial regression is usually done on a software. How do you sort of, account for spatial effects is all done on a software. But it is equally important to learn the theory, just like in case of kriging, in case of the variogram. Although everything is highly computational and it's very, very important to learn the software, at least as important to learn as it is important to learn the theory if you are to actually use it for any practical purposes. But the theory is very, very important as well. Okay, so I hope this lecture was, was fun for you, and I look forward to having you in the next module, which is called as spatial econometrics. Thank you.